first, okay, I want to review a little bit what we did in the last lecture, right? So we're on the same page. Okay, so first, the relationship between problems and decision problems. Okay, what's the problem? A problem, you can think about a problem as a mapping between an input and an output. You give me, you give me an item. For example, if I ask you a question, what's 2 multiplied by 2? And you give me 4, so input, output, right? And it turns out that every problem you can think of can be modeled as a decision problem, okay? So if you have whatever problem you have, for example, how to get from Plymouth to London in the shortest time. Okay, that's a good problem. You have only one possible answer here. So you can model the problem as being, okay, is X the shortest path from Plymouth to London? And then you input X, and you say, okay, start from Plymouth, go to Rome, then to London. No, it is not the shortest path. I start from Plymouth, go to Bristol, and then to London. Yeah, maybe, I don't know. I don't know what's the shortest path, okay? So all problems can be simplified to decision problems. And that's good, because if you do that, in the end you get a set of right answers. And by studying that set, you actually understand what the structure of your problem is, what's the skeleton, okay? How to treat your problem computationally, okay? So you have that set, you see that it has some kind of structure. For example, the only structure we know of, as for now, is the regular structure. So if you understand that your problem, so you get your problem, you make it into a decision problem, yes or no answers, right? You get this set of the right solutions, and you study this set. And you see, oh, this is regular. Perfect. If you show this, it is regular, you know you can treat it with deterministic finite state machines, which we saw yesterday, right? That's very good, because that tells you something about the problem, which is that you don't need infinite memory for your problem, but just finite memory to solve your problem. And it means that, for example, if you want to program, to program an algorithm to solve your problem, you can just make a lookup table, okay? Which is pretty good. Some of you asked me to make more real-life examples. There are plenty of real-life examples with regular languages and deterministic finite state machines, lookup tables. For example, when I did my master's in robotics, we had these little walking robots, right? And they were really simple, okay? You wanted to keep the hardware at the minimum, of course, right? And the hardware that was there, you wanted it to solve some problems, so to reserve more computation to solve some problems and less computation to solve other problems. One of the problems you really didn't want to think about was walking. Okay? So these robots, in their controller, they had a simple lookup table to say, okay, do this movement here, do this movement here, okay? You're solving a problem, okay? You're walking, and you're solving it with a lookup table. That's really nice, right? Because it means that by doing that, you don't have to compute dynamics, or you can pre-compute everything before, then put it into a robot. The robot will work, and it won't. You won't need a i5 Intel quad-core processor to do that. Okay. So this was the DFA, if you remember. So what's a DFA? I'll give you the formal definition, so you're sure to know the formal definition of a DFA. A DFA is a 5-tuple, right? Okay. It means that it's a collection of 5 things, basically. The 5 things are, you have a set of states, so a collection of possible states, and here you have 8 states. Then you have an input alphabet, which is just an input alphabet, okay? And, well, yeah. If you wanted to recognize strings from English, your alphabet could be the entire English alphabet plus numbers, plus, I don't know, exclamation point, Okay. Then you have to set an initial state, meaning, okay, I'm starting to solve this problem. Where am I? Okay, you're in the initial state, and the way you draw the initial state is just by saying, okay, there's an arrow pointing to the initial state. There's no transition here, there's no symbol, just an arrow. This tells you 1 is the initial state. Okay, let's talk about the symbology so we get this straight. Okay, so if I define a set like this, are you comfortable? I mean, I'm saying Q is a set of states. You understand it's a set because it has these curvy braces. And then you have the elements in it, and that's a set. Okay? So that's a collection of things. Same here, the input alphabet is just a set. As we learned, is a set of symbols. The initial state is a state belonging to Q. You have the symbol there, right? So Q belongs to Q is the initial state, and Q, well, I call it Qi, like Q initial, is equal to 1. So the element is the first state. And then you have a set of accept states, which is a subset of this one I didn't write. So if I write a proper subset of B, it means, okay, basically that if this is the set B, this is A, okay? It is possible also that A is the total, I mean, it's all of B. Okay? So when I say this means subset. Subset. Okay? So you have a subset of accept states, which mean if I input a string to my DFA and I end up in a state which is an accept state, then my string is accepted, meaning the string is a solution to my original problem. Okay? And then you have a transition function. Okay, this one I didn't really explain to you last time. This terminology here, these symbols here mean delta is the transition function, and delta maps elements of Q paired with elements of the alphabet and gives in return another state, Q. What does it mean? Okay, if you're, so delta, start with a Q. So you're in state 4, okay? And now you want to know, okay, if I'm in state 4 and I input the symbol F, what do I do? Nothing, there's no transition, okay? If I'm in state 4 and I input the symbol E, okay, you go to state 5, okay? So you give the delta function a state, you give the delta function a symbol, and the delta function gives you back a state, okay? So that's what it means to be a 5-2, okay? So alphabet string languages, you seem pretty comfortable with them, but we will see them a little bit just now. So an alphabet is a set of symbols. A string is a set is a sequence of symbols from an alphabet. So you get an alphabet, you can build your string from the alphabet, and from the set of all strings, you choose some, and from that you get a language. So a language is a set of strings. Okay. Actually, if I want to say that a string is in a language, I can use the terminology word. So S is a word in language L. Okay. Now I want to have a look at the again at the operators on sets. Okay, so that you know how they work. I want to do some examples. So let's say that A is equal to 0, 1, 2. B is equal to 0, 4, 80. Okay, these are all symbols. Actually, I'll choose 8. So you know, you don't get confused. So if I say, for example, what's the union of A and B? So union of A and B means I take all the elements from A, I take all the elements from B, and that's my set, my union. Of course, if there's some element which is repeated, you don't put it in the union set, because that element you already have it. Okay. So A union B would be 0, 1, 2, 4, 8. Okay? So that should be pretty simple. Z, Y, X, A, B, A, C, D. Okay. So, if I ask you to find me the union of A and B, okay? So, write me out.
Z, Y, X, A, B, C, D.
Yeah. Is everybody comfortable with that?
Sorry, can you repeat? I couldn't hear that from it.
Sorry?
I couldn't hear that from it.
Oh yeah, that's all right. Wait, you had me out. So, what are the elements of A union B?
A, B, C, D, Z, Y, X.
Z, Y, X. Exactly. So, even if you didn't hear it, it's exactly what it said. So, I guess that we're okay with it. We can. So now we do concatenation, okay? Let's use other symbols. Duck, bay, I really not be equal to mouse, and key. I don't know. Okay, let's say I want the concatenation of A and B. So A, B is equal. You get a symbol from A and you combine them with all the symbols from B. You get a symbol from another symbol from A and you combine it with all the symbols from B. So it will be duck, mouse, duck, key, bay, mouse, bay, key, which doesn't make any sense. Okay. And that is the concatenation of A and B, right? So it just means do all possible combinations of elements which start from A. So you get duck, and then you combine whatever you have on B. Then you get bay, and you combine whatever you have on B. Okay? This is the concatenation of A and B. So if I ask you, the concatenation of B and A, can anybody give me an element from BA?
Mouse duck.
Mouse duck, exactly.
Mouse bag.
Okay. Mouse bag.
Key duck.
Key duck, exactly. Last one.
Key bag.
Excellent. Key bag. And this is the concatenation. Just to make sure you don't get confused, if here I had duck, okay, I would actually concatenate duck. So if I had AB, for example, duck would be a word in AB. If I have BA, duck is a word in BA. Okay, so it's different from the union in that. In the union, if you unify two sets which have an element in common, that element shows up only once. Instead, in the concatenation, you actually concatenate. So you see what I mean? Okay, that's the concatenation. And last, the mouse. last one, clean star. The clean star means, well, I write down the definition, okay? 0, A1, A2, where this means AA, A3, A, okay? So this one is defined to be the set containing the empty string. So whatever set you have, which is exponentiated to 0, is the empty string. Okay. This means this means the original alphabet or the original set. Okay. A to the second means a concatenation of A and A. So you get duck, 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 bay, duck, mouse, bay, duck, bay, 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 mouse, mouse, duck, mouse, bay, mouse, mouse. Okay. A3, duck, 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 bay, duck, duck, mouse, duck, bay, mouse. Okay? You see where I'm going? You just, yeah.
Can you give an example of doing that with numbers as well?
With numbers, yeah, of course. For example, yeah, I have a nice example. 1, 2, 3, blah, 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 9, 0. Okay? This is a set of all digits. Okay? So if I do the clean star on this set, what I get is the set of all positive numbers, because, well, plus the empty string. I have the empty string, then union, meaning that I'm, union. A to the 1 means the original 1, 2, 9, 0 set, union, all the combination with two symbols, 1, 1, 1, 2, 1, 0, actually you have also 0, 1, 0, 2. You see where I'm going? So you get the elements and you combine them 2 by 2. And you get all the possible elements of length 2. And then you get all the possible elements of length 3. And then all the possible elements of length 4. And you do the union, and that's your clean star. So, oops. If I have, for example, BA, okay? What's the clean star of BA? What's the first element of this new set?
Empty string.
Empty string, perfect. Second one?
B.
B.
A.
A. Then?
BA.
BA.
BB.
BB.
AA.
AA. BB. A, blah, blah, blah. Okay? So you get where this is going. And this is the clean star. Okay, so you should now know that. Sets operation, non-deterministic finite state automata. I told you that. So non-deterministic finite state automata have exactly the same power as finite state automata. What's a non-deterministic one? Basically, okay, with the finite state automata, you have a machine which is serial. So you have your machine, you give a string to as an input, and your machine does like this. State 1, I received B, I go to state 2, I receive C, I go to state, and that's a sequence, a deterministic sequence of states. The non-deterministic machine instead can go to 2 states at once. It's like spanning parallel processes, right? So you do 2 computations at once. So you receive A, and you go to state 1 and state 2. And then you receive B, and maybe state 2 will go somewhere, and state 1 will go somewhere else, okay? And then maybe they will span other processes, so you have 4 states computing your input stream, okay? So it's like a parallel processor, but it turns out that whatever NFA you can throw at me, I can convert it to a DFA. So they have exactly the same computational power, exactly the same, you can solve exactly the same problems. Then the relation between regular languages, regular expressions, and DFAs. So this is the relation we're talking about. So as I told you, a regular language is like a set of the solutions of your problem which have this regular structure. So the regular language is the most primitive, let's say, the most important object. But you can represent a regular language in many ways. You can represent it as a set, so with this notation here. So you can say that your regular language is the language. Each element of the regular language is such as this element ends with 0, and that's a regular language. So you're expressing it as a set. Or, to define a regular language, you can build a deterministic finite state automaton. What does it mean? That your deterministic finite state automaton, for every string you throw at it, it either accepts it or rejects it. So if you take all the strings which are accepted, that's a regular language. Now, why do I say that the regular language is the most primitive object? Because you can have many DFAs which recognize exactly the same language, okay? And the same with regular expressions. You can build a regular expression representing a regular language, but you actually can give many more. You can give many regular expressions which are representing exactly one regular language. Okay? So that they are equivalent. You have many equivalent regular expressions, many equivalent DFAs, but you have only one regular language with some characteristics. If you have two, they are the same. So they're not equivalent, they're actually the same. Okay? So now, this was the last lecture. So with that, yeah, I'll show you finite state transducers. So for some problems, DFAs are not the best way to solve a problem, right? And there's another model which is used in programming, for example, and it is helpful to know about it, which is the finite state transducers model, which is simply a finite state machine, a deterministic finite state machine, which doesn't have any accept state, but at each transition, the machine does something. It outputs a symbol, or if you program a coffee machine, it does an action, like giving you back change or displaying the reminder or giving you coffee. Okay? So for example, we want to build a coffee vending machine in which you pay your coffee for 40p. This is my dream at my office, but it won't happen. And it accepts only 10 and 20p. The machine produces coffee only when the full amount has been paid, and that's normal. If you don't do that, your client would be really pissed off. The machine gives a change. There's an abort button, meaning that, for example, if you have only 30p and you realize at the last moment, you press the button and the change goes back to you. It displays reminder when money is inside. So let's see how to do it. So 0, 10, 20. So I will build it, and so for example, you input 10p, 10 pence. The machine displays that you still have to give it 30. So this is the notation. At each transition, you don't just go into another state. You also output something with this finite state transducer. So I give 10 pence, then machine displays 30 pence. Okay? I give other 10 pence, machine displays 20. I give 10 pence, machine displays 10. And if I give another 10 pence, So here I've written the amount of money that is in the machine at this particular moment, right? If I input other 10 pence, the machine will give me coffee, okay? Because you paid the 40 pence, okay? So 10 pence, coffee. Okay. And then the machine also accepts 20 pence, so I will do the same like here. So 20 pence, display 20. Okay. So for example, if I put an abort button, I will have some transitions like that. So I am at 20, the abort button will abort will give me back my 20 change, 20p change. So you see what the concept is of finite state transducers. Instead of having only transition from state to state given an input symbol, you also output something in some output tape, or you perform some action. And you can see this is useful in programming. You know, if you ever use, for example, in C, the switch statement. It's like the switch statement is if you nest switch statements, you get something that resembles a finite state transducer, right? So this is something it's nice to know if you'll ever like to use it. So finite state transducers, and now, okay, now for the interesting part. So the DFAs are a computation machine, okay? The automata means machine in, I think, Greek, and they're a model of computation, okay? Meaning that they help you think about some problems, they help you build software, they help you actually think about computation, okay? And in the case of DFAs, the DFAs give you the chance to think about what are the characteristics of the problems which can be solved with a finite amount of memory, okay? But it turns out that some problems you cannot solve with just a finite amount of memory. Meaning that if I give, for example, I cannot give you a machine, a finite state machine, which can balance parentheses in some code, okay? It seems like a very simple problem. Okay, you write your C code, you forget a parenthesis, and you want your IDE to add inside a finite state machine which tells you, hey, you forgot a parenthesis. It turns out that you cannot just build a DFA which solves this problem. Because this problem needs a variable amount of memory. Okay, it's not something you can set and then forget about it. You need a variable amount of memory. So DFAs cannot solve that. Well, actually, as DFAs are a model of computation, you could discover that, well, I think all physical problems can be solved in a finite amount of memory. Because there is a finite set of states to physical reality. Well, maybe, we don't know yet. For example, if I gave you a computer and you have a terabyte of data, here I express it in decimal because I don't want to do the 1024, the powers of 2 thing. If I give you a computer, you have an hard disk, it has a terabyte of data in it, right? And the computer at each step of the computation basically reads something from the hard disk or the RAM, let's say that all memories in the hard disk, okay? And makes a decision out of it, which is deterministic. So if I have a 0 and 1 here, my next state will be, I don't know, write 1, 0 there. Okay, the processor that does this. So it's a deterministic computation. So you can actually calculate the number of states inside a PC, which is more or less 2 to the 800 millions. Yeah? So 2 to the, no, 8 billions, what is that? So 100, a million, a billion, 800 billions. Is that right? Okay, a lot. A lot of states, okay? And if you do the math, you discover that the number of atoms in the universe is 10 to the 78, which is more or less 2 to the 259, which is much less than this number here, okay? So you could, in theory, model a computer with a DFA, and it could be useful for some problems. I cannot think of any, but maybe it could be useful to treat the computer as a DFA. But it's very expensive and probably won't lead you anywhere. So even if in physical reality most problems, or maybe all of them, require only a finite amount of memory to be solved, that doesn't mean that we should use DFAs for every problem. And actually, it's useful to think about some problems in a more abstract way. For example, the parenthesis balancing problem, okay? So I want a machine that tells me if I close all my open parentheses. Maybe I can do a DFA which can memorize, so has enough memory to remember 1,000 billion, trillions, millions parentheses, open parentheses. So I can do that. But that doesn't mean that that is the best way to go about it, okay? So, some problems need an unbounded amount of memory to be solved. Meaning that not that you would have to have a computer which runs forever, but just meaning that, for example, to solve the parenthesis balancing problem, you cannot just set a finite amount of memory and stick with it. You need an algorithm that can allocate memory and use, the needed one. Now, so some problems require counting, like the parenthesis balancing problem, meaning that you have to count, for example, the open parentheses to know how many you have to close, right? And if you discover a problem which requires counting, you can say that it is non-regular. But some problems may look non-regular, but actually that's just because you didn't find the right algorithm to solve it without using an unbounded amount of memory. For example, two of these problems are non-regular. So the first problem is the word in L0110 has an equal number of 0 ones and 10 substrings. It looks like you have to count them, right? Because you have to count, okay, you have 10 zeros and you have to count 10 0 ones. Language 01, word in this language has an equal number of ones and zeros. This really looks non-regular. You really have to count, it seems, right? The last one, W is equal, so a word in this language is equal to n zeros followed by n ones. Okay? They all look non-regular. But actually you have an algorithm to solve the first one with finite memory. So it turns out it is regular. So intuition, you cannot just rely on intuition to say that a language is non-regular, okay? You need something more powerful. And you do have it. You do have something more powerful. And this is what it is called in computation theory, the pumping lemma. So what's the pumping lemma? The idea is this. Okay. The idea is like that. If you have a DFA, right? If you have a DFA, you have a finite number of states. Let's say that you have 1, 2, 3, 4, 5, 6 states. Okay, if you have 6 states, if you have a string of 60 characters, that means that somehow inside the DFA you have to loop, Okay? So if your string is accepted, it means that somewhere inside the DFA, you have to go through a loop. So for in this example, A, B, A, B, B, A, you have six symbols. So A, B, A, B, B, A. Yeah. As you see, here you have a loop. And in that loop, you can pump part of a string, in this case, B, A, B, B, how many times you want, okay? So for example, A, B, A, B, B, A is in the, so this is an accept state, is in the language, A, B, A, B, 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 A, B, B, A is in the language, A, B, A, B, 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 A is in the language, okay? So you can pump this B, A, B, B how many times you want, and it will still be in the language, okay? But this is the only way you can have strings which are longer than the number of states in the DFA in a language, meaning that you cannot have a string which is 60 characters long with a DFA with 6 states and not have a loop in your string. You see what I mean? You cannot have that. So this is the idea beyond the pumping lemma. So the actual statement, the actual definition of the pumping lemma is if a language L is regular, then there exists that A, inverted A means exist. There exists P belonging to the natural numbers, meaning that for every language, I can choose a pumping length, which normally you would make it coincide with the number of states in your DFA, such that if S is a string in the language, and the language and the string is longer than the number of states in the DFA, then S must be composed of X, Y, Z. Okay? The idea is that this Y is where you have the loop. So this Y you can repeat how many times you want, and it will still be in the language. So that's what it means, this E, this I here, right? So X, Y, 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 Z is in the language, X, Y, 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 still in the language, okay? The length of X and XY is at most P, meaning that you don't loop before. You don't loop before reaching this string here. And the length of the looping string is more than 1, meaning that there is a looping string. So if the length was 0, then it wouldn't have been existing, okay? So, for example, what does this mean? Let's take as an example that language I told you before. So the language is 0 to the n, 1 to the n. Is this a regular language? Turns out it is not. How can I prove it? I can prove it by saying, okay, these strings look something like this. Okay? So you have the same number of zeros here, the same number of ones here. Now, so because they're infinite, right? So you can choose that n. You can choose whatever n you want. Your DFA must be able to recognize all of them. But that means that I can choose P, for example. let's say that my DFA, the DFA that recognizes the language as a P states, then I can choose a string, 0 to the P, 1 to the P, and you know for sure that because you just have P states, you have a loop somewhere here. So somewhere inside this string, your DFA is looping, okay? But this is impossible. Why is that? Well, okay, let's say that the loop is somewhere on the side of the zeros, okay? So you do your 0, then you have a loop 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. You exit the loop, you do the ones. That's not possible. Why? Because if you pump that string, you're adding more zeros, but you're not adding more ones. And so your string is not in this form here. You have more zeros than ones. Okay, so this doesn't work. Let's say you have a string in the side of the ones. Well, it's the same kind of reason. If you pump this string here, so you do 0, 0, 0, 1, 1, 1, 1, 1, 1, 1, how many you want, how many you want, how many you want, and then you finish with 1, 1. Again, it's not a string in this language here, because there's more ones than zeros. Okay, you only have you have only one last choice. Your string is somewhere in the middle, so you have some ones and some zeros. But if I pump this string here, 0, 0, 0, 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1, for example, and then I go with 1, 1, 1, okay? This is not a string in the language, because you have this weird thing here. The strings in your language are just zeros and ones. There's no 0, 1, 1, 0, 1, 0, 1. So I have shown you that with strings in this form here, you cannot build any DFA recognizing all of them, because you really cannot find any way to loop and so to use a finite amount of memory to recognize all of them. Have I convinced you? Let's start again. So I'll try to rephrase my definition of the pumping lemma, right? So what the pumping lemma means is that okay, you have a language and you are saying it is regular. If a language is regular, it means that you can build a DFA recognizing the language, right? So if you can build a DFA has a finite number of states, right? Okay, let's say that your DFA has P states. Okay, P is a number, whatever number. We don't know the number. We're just saying, okay, that my language is regular. I have my DFA. My DFA has to have a number of states, and let's say this number of states is P. Okay. Now I'll tell you about the pigeonhole principle. The pigeonhole principle, which is just saying if you have 7 pigeonholes and you have 8 pigeons, that means that a hole must contain 2 pigeons, okay? Because you just have 7 and 8 pigeons. Now this is the same principle. Your DFA has P states. Okay, let's take a string in a language, in this language, which is infinite. Let's take a string which has P plus 1 symbols. Then, by the pigeonhole principle, that means that somewhere inside your DFA, you're going, you're using the same state 2 times, okay? Because you have P states, you have a string of P plus 1 symbols. Somewhere in between the DFA, you're looping. In the most economic case, you're just revisiting a state 2 times, but it can be more, okay? Meaning that your loop could be, I don't know, you're visiting the same 5 states a lot of times, for example, right? So if you have a string which is longer than P, of course you have to be looping. So if I want to prove that a language is not regular, what I have to do is take a string which is longer than P and show that nowhere inside this string I can pump So I cannot loop anywhere and still be in the language. The example I showed you is the example of the equal number of zeros and ones. Okay? If I add stuff anywhere, if I pump from anywhere inside the string, then the new string is not in the language anymore. So there cannot be a DFA which recognizes it. Okay? So because there's no DFA, then the language cannot be regular. Because as I told you, the regular language can be represented by a DFA and by a regular expression. Of course, if you cannot do this representation, it means that your language is not regular. Okay? So if your language doesn't have the pumping property, it means that it is not regular. That helps you only sometimes, meaning that your language could have the pumping property and still be not regular. Okay. So an example of this. So if I say a language, okay, all regular languages have the pumping property. That means if a language doesn't have the pumping property, then it's not regular. But that doesn't mean that if a language has the pumping property, then it's regular, okay? And this is the same. So all cows are vegetarian. This animal is not vegetarian, so it cannot be a cow. But I can think of another animal which is vegetarian, but it is not a cow, maybe. Always kind of hard to tell. So, what we did today, we reviewed. We saw finite state transducers. I showed you the limits of the DFAs, which will bring you to our next subject in the next lecture. So, there are some problems which cannot be solved with DFAs. We need something more. And what we will do is provide our DFA with some memory. So you have a stack memory. So you can put symbols. You can pop. You know, you use a stack, right? So it's a first in, first out, right? First in, first out. Yeah. Okay. So that we'll see in the next lecture. So what happens if we give a DFA some memory? It can solve a lot more problems. Actually, another thing I want to tell you, talking about applications of what we're doing here. If you have a compiler, okay? If you have a compiler, the first step of your compiler is to catch the keywords inside your program, right? And this is the perfect problem to be solved by a DFA. So in the first stage, what your compiler is doing when you compile your code, it takes your code, so your code is some text. It tries to figure out where the keywords are, and it parses the file trying to look for keywords. Okay. So, and this is called well, it's parsing. Parsing, which is done with DFAs. Syntactic analysis. I don't really remember, but basically the concept is that at the first stage you find the keywords, and then you try to figure out how these keywords interact with your variables, and what's the actual syntax of your code, and that is done with PDAs. Okay, so what the DFAs like this. So if you learn a language, first you learn the words, and that's something that you. Okay.
Lexical analyzer.
Exactly. Thank you. Yeah, it's a lexical analyzer. So exactly, when you learn a new language, the first thing you do is learn the words. Okay. So you read the words and you remember. Okay, this is a word I remember, and that's a DFA. So you scan the word, you parse the word, and you say, accepted, this is a word of the new language I'm learning. The next step is, okay, how do I combine these words to form phrases, okay? That's the syntactic analyzer, the next step, which is done by PDAs, so push down automata. We will be talking about it in the next lecture. So, some exercises. Now first let me delete this. Okay, define a DFA. I already did it today. So a DFA is a 5-tuple. So states, initial state, final states, delta function, and input alphabet. 5 items. So you may want to remember that. Okay, now let's actually build these DFAs so we see how they work. So the alphabet is X, Y, Z. You also have to specify an alphabet. Okay, your DFA works on an alphabet. Be the DFA accepting the language of strings ending with YZ. So in set notation, language YZ is the set of the strings which have the property that these strings end with YZ. Okay? This is how you do it. So the alphabet is X, Y, Z. So your initial state, so you want to end in YZ, so Y and Z, okay, and this is the accept state, so your word must end with YZ, and so here you can have all the X's you want, X, Y, X, because, okay, it has to end with YZ, right? So if you do, for example, YX, you're not in an accept state, so you must return. Here, YZ, so here you can return, okay, meaning that if you do Y, you still could end with the Z, right? Again, Y. Here, if you mess up, Z. Here, Z. So basically, you can think about it like a, so here, the string is yet to be formed. Here you have Y. Here you have actually YZ, okay? So at every step of this DFA, it's like you're remembering that something, you're remembering part of your string, right? So here you don't have a string, so you could do X, 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 Z, 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 Z. It doesn't matter, it's not ending with YZ. So if you go to a Y, then maybe you could be onto something, okay? So Y, if you have said you're happy, and you're happy, but you could have an X, so X, no, you have to start again, you have to wait for another Y to go to Z, okay? So again, that is the initial state, that is the accept state. So if we want to write down our states, we could call them epsilon, sorry, Y, YZ, though that could be confusing. I only did it to show that at each step of this DFA, we're building the DFA, so we're building the string, so we could do just this. It's less confusing. So you have this. What's the input alphabet? X, Y, Z, exactly. Z. What's the initial state? Sorry? Yeah, I changed it to small. Okay. What's the final state? Exactly. We write it like this. Because actually, okay, while the initial state is only one, always, you always start with a single state, from a single state. The final states, on the other hand, could be more than once, could be more than one. So the initial state is just an element, while the final state is a set. So we actually denote it like a set. Okay. Now in this case, it has only one element, but in many cases it could have more. Okay? This is one. Okay. So 0 and 1, the alphabet is now 0 and 1. With a DFA that accepts the language of strings starting with 0 or ending with 1. So this is actually simpler than the first one, I think. So this is the first state. You want to accept a string if it starts with 0 or if it ends, right? If it ends with 1. So help me out here. So if it starts with 0, we've already done. Our computation is done. So if we receive a 0 there, we just accept. Okay? So we enter in an accept state. And then whatever happens at that stage doesn't matter, because we already have our 0, our initial 0. So whatever, if I receive a 0 or a 1, it doesn't matter. I just stay in the final state. Okay? So here we're accepting all the strings which start with 0, and we're happy. But we also want the strings which end with 1. So this is, let's call it 3. So let's say that our string starts with 1, we accept, if there's nothing else. What if there is something else? Well, then you could have a 0, and in that case, our state, would this state be accepting or not? Exactly. It's not accepting, because we want our string to end with 1. So we go here, but we want to accept only if then there is a 1. Okay? Actually, there's one more thing. What do I put here? So our string could be 1, 0, 0. Exactly. Any number of 0. The important thing is that it ends with 1. Okay? So this is a DFA recognizing the language of all strings starting with 1 or ending with 0. Easy, right? So what's our initial state? 1. Exactly. What's our final state?
7.
Sorry?
The set of 2 and 3.
Exactly.
Doesn't at 3, does it not need to loop around for adding more 1s?
You're absolutely right.
Cool. Thank you.
Yes. Whatever 1 you add, in fact, it will still be ending with 1. Okay then. Alphabet is 0 and 1. DFA accepting the set of strings which with an even number of zeros, right? So I start with state 1, which is an initial state, and I denote it like this. So we want an even number of zeros. We don't really care what happens to the ones. We're just making sure that the number of zeros is divisible by 2. Now this is a good example of a problem which you don't need infinite memory. You just have to be able to count 2. Okay. Because if your string is 4 zeros, you do this is accepting 1, 2, 3, 4. Okay? And you're accepting, and you need a finite amount of memory. So, an even number of zeros, right? Okay? You can do this. Write down this up. Oh, actually. Okay. You want an even number of zeros. 0 zeros, no zeros at all, it's even. Because it's a multiple of 2. 2 multiplied by 0 equal to 0. So this is an accept state. Then if you input a 0, you're not accepting anymore because you have 1 and it's odd. So you have a state here which is just saying, I've only seen 1, 0, so I cannot accept. What do I put here? So I'm counting. I want exactly 1. So I can have only all the ones I want here, right? The only thing that is important to me is to wait for another 0 to appear, so I can go to the accept state, and I can say, yes, I have an even number of zeros. So what symbol will be there? Okay? So again, the initial state is 1. What's the final state? 1. They can coincide. It's not a problem. Okay? Okay. Let's do some more. Okay. Let's do it. Let's complicate things a little bit. So, 0 and 1 is the alphabet. The language is the strings which have an even number of zeros and an even number of ones. So again, you can see that with this problem you don't need unbounded amount of memory, right? You just have to count that you have a number of ones which is divisible by 2, so you actually need like 2 bits of memory to check for that, right? And the same with 0, okay? So your memory is always bounded. So let's build it. Even number of zeros, even number of ones. So again, the first state is accepting because no zeros and no ones is even for the zeros and for the ones. So I may want to have the same machine I had before with ones. So this checks here that I have an even number of ones. Here I check that I have even number of zeros. But actually, here I could be adding zeros to the string. Okay, so not all strings are just 1 1 1 1 0 0 0 0 or 1. Okay, so from here you do have a transition. You do have to have a transition with a 0, right? So I will do like that, and the same goes for here. And you can check whatever string you can think of that does even number of zeros and ones will be accepted by this machine. So let's say, well, I'll make one up now, right? So 1 1 0 0 I don't know 1 1 0 0. Okay. So 1 0 0 1 0 1 1 0. I start from state 1. I'll number them now. 1 2 3 4. So 1, and I go there. 0 0 1. Oh, sorry. 1 0 0 1, right? Then a 0, 1, 1, and 0, and it is accepted. Okay? So every string will follow that pattern. Okay? So I think you more or less get the gist of it. I have more of that, but I only have up an hour, so let's do this one. Okay. So another language defined on the alphabet 0 and 1 is composed by all the words, all the strings which have this property, so that the string has length at least 3, and its third symbol is 0. So meaning that, first of all, we want four states. Why do we want 4 states? Because we have to make sure that our string has length at least 3. Was it at least 3? Yeah, at least 3, right? So our accept state will be here, okay? So something happens here, something happens here, something happens here. I know now that I counted 3, okay? So I'm counting with this DFA. And now let's see what happens next. So this is 1, this is an accept state, let's call it 4, 3. So the third symbol is 0, okay? So the first one doesn't matter, 0 or 1, oh sorry, this is the initial state, so don't forget the arrow of saying that this is the initial state. So 0 and 1, okay, we're right, still in the language. 0 and 1 is in the language. So the third symbol must be 0. So if this happens, we're happy. And then, what do I put here? 0? 0, 1. Because once we're reached state 4, we know that the string has length 3 or more. And then we can just stay there because the string is the string is longer than 3, and the third symbol is 0, so it stays there. Of course, here we cannot forget that if the third symbol is not 0 but it is 1, then we cannot accept. Okay, so we stay here forever. It's a dead state, sync state, a state which is not accepting, and you are stuck there forever. Actually, I want to show you that you can represent exactly the same language with a regular expression. Okay, so really those are exchangeable in a sense. So you can use DFAs. So you would use DFAs more to actually do the computation. Okay, to actually show how to deal with your problem. What are the steps involved to solve your problem? Whereas the regular expression is a way of expressing your language, okay? Which is useful. Well, for example, I use it a lot on Emacs. I showed you egrep, and they're actually very useful once you know how to use them, and once you recognize the problems that you can solve with regular expressions. They're everywhere. They're they're super optimized now. I don't know, every piece of every programming language is a declination of regular expression. I know Python has regular expressions. Pretty sure C++ has regular expressions. Java, I'm sure it has regular expressions because it's really useful to have them. So, how to express this as a regular expression? Ooh. Okay. Okay, first, I want to remind you what a regular expression is. So you have an inductive definition. But basically what you need to know is that a regular expression is something of the form, you really need the inductive definition. So every element in your alphabet is a regular expression. If you concatenate two elements, that's a regular expression. If you group them, regular expression. If you do the clean star, it's a regular expression. If you do the alternative, it's a regular expression. And now I will show you how, otherwise, of course, how can you understand? So let's transform this as a regular expression. So at the first step, you want a 0 or a 1. So you can write 0 plus 1, which means 0 or 1. Or if you prefer, you can use the logical OR, which is like this. Okay? But the important thing is that you stick with the notation. So I'll just use the logical for. So the first step, you have a 0 or a 1. At the next step, you have a 0 or a 1. Then you have a 0, because your third symbol must be a 0. And then you can have whatever you want. Oops. Okay? So this is a regular expression, right? So, as I told you, inductively you can say this is a regular expression, this is a regular expression because they're elements of your alphabet. They're alternatives, so 0 or 1 is a regular expression. The grouping is a regular expression. Concatenation, so you're concatenating here, is a regular expression. And clean star of regular expression is a regular expression, so this is a regular expression. The inductive definition, well, it's useful when you want to transform your regular expression in a language, for example. But in this case, it's very clear. For example, if I did this string wouldn't be a regular expression anymore because, well, what's this about, okay? So it's easy to spot a well-formed regular expression. So let's do more. So, is 0 or 1 a regular expression? Yes. Thank you. Is 0, 1 a regular expression? Yes, it's a concatenation. And now we'll write down some regular expressions. Okay. Make sure I don't mess up. Okay, strings starting with 1, 1. Well, 1, 1, and then 0 or 1. I'll put the logical forward to be consistent. Repeat it how many times you want. So what does this mean? Your string starts with 1, 1, and then you have 0 or 1, and that repeated how many times you want. Meaning that at each step you can do 0, 1, then the next step you can do 0, 1. So 0, 1 is captured by this. 0, 0, 1, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 1, 1. Everything is captured by this, okay? So your string is a string starting with 1, 1 and ending with either 0 or 1 or all possible combinations. Ending with 0, 0. So can you help me out with this? Now you should be able to tell me.
2 brackets, 0 or 1 star, 0, 0.
Exactly. Very good. 0 or 1, 0, 0. Oh, forgot the clean star. Okay? Starting and ending with 1.
It's like 1 bracket, 0 or 1 clean star, or ending with 1.
Exactly. Starting and ending with 1. So you can have whatever you want here, so 0 or 1 at each step, and then you can do 0, 1, or can have a 0 or 1, 0 or 1, 0 or 1. The important thing is that you have a 1 at the beginning, 1 in the end. That's a regular expression, and it expresses a regular language, which of course can be recognized by DFA. Start with 0 or terminate with 1. So, okay. Let's see if you can solve this one. So this is just a step further from the previous ones. So it either starts with 0 or terminate with 1. So we know there's a 0, and then what can you have?
0 or 1 star.
Perfect. 0 or 1 star. But you can also have strings which terminate with 1. So you can say or 0 or 1 star 1. Okay? So let's do some more. This is matched with the DFAs. Okay, so the language contains all the strings which have as substrings 0, 1, 0, 1. I don't think I told you what a substring is, but it's very easy. So if Giovanni is a string, then NNE is a string, then VAN is a string, is that a substring, sorry. G is a substring. You see where this is going, okay? So you just grab substrings from the string. So I want a regular expression which contains the string 0, 1, 0, 1. How do I go about it?
0 or 1 star, 0, 1, 0, 0, 1 star.
Yeah. So, John, can you help me out with this? So we want it to contain 0, 1, 0, 1, right? So 0, 1, 0, 1 has to be in the middle. What do we start with? It's okay, don't worry. Okay, I don't want to put you under pressure. It's all right. But yeah, so you can have whatever you want in the beginning, okay? The important thing is that you have 0, 1, 0, 1. And then you can end with whatever you want. Okay? I don't think I will do this. Okay, because of that inductive definition we saw, it's actually pretty straightforward to find a way to go from a regular expression to the set. The set is the regular language. Okay? So it actually completely is completely symmetrical. So let's say that L is a function which brings us from a regular expression to a set. Okay? So L of the empty set is the empty set. L of the empty string is a set containing the empty string. L of whatever symbol from our alphabet is a set containing that symbol. L of a grouped regular expression is just L of the regular expression. L of a starred regular expression is the language of the regular expression starred. L of the concatenation of the regular expressions is the concatenation of the languages of each one. L of the alternative is the union of the two languages, okay? So, okay, this is the definition, and I can use it to actually start from a regular expression and end up with a language. So, again, I don't want to mess up. So, I will. So, okay, so this is the regular expression here. What I want to do is end up with a set. So, the first level, the first thing we see is that we're concatenating three strings, right? So the concatenation of this regular expression is the concatenation of the sets. So here, this is L of L1. Okay? Then the clean star of the regular expression is actually the clean star of the language. So it's like we just take the clean star outside. So here, this L, this is actually a language. This is telling me the language which has as only element 1. This is the language that has as the only element 0. And we want to end up with the function L all in this form. Okay? So we're going in reverse with the recurrent definition which I showed you before. So we want to go from the complex regular expression back to the simple regular expression, so the symbols, okay? So what we do here is L0, L of, well, the alternative here, right? So it has to be, just write it L of 1, 0, union L 0, 1, and this is start L space 1. Then okay, we just continue, and well, I might as well finish. This is L1, L0. Union L0, L1, start, and okay, here, as you see, we reached the elementary symbols, okay? So here our expression is now L0 concatenated to L1, L0, union L0, L1, clean star L1. So we can go to the set now. This is equal to the set 0 concatenated with the set 1. Oh, this is another set. 1, 0, union 0, 1, start. This is getting a little messy. But this was just to show you that from a regular expression, you can go back to the regular language. You won't have to do that anywhere. So, it's all right. I just wanted to make sure that you understand that the regular expressions, DFAs and regular language, you can go, in this diagram, you can go from everywhere to anywhere. So you can go from a DFA to a regular language, from the regular language to a regular expression, from the regular expression to an NFA, to the NFA from, they're all related. They all talk about the same object. So I think this is enough for today. I'll see you next time with the PDA, so the push down deterministic algorithm. Okay?